Hello folks, and welcome to Rational Science. Today we're going to be talking about this gentleman. His name is Peter Woit, and he's an expert in twistor theory. And I mean, he's an expert. I mean, if you're going to try to find out something about twistors and especially the math that's behind it, he's the man to see and he's the man to hear, okay? And so let's look at a little bit of his bio, okay, here. He's a mathematical physicist. He's been at Columbia University for about 30 years now, and he's a PhD in particle theory from Princeton. That's where he got his PhD. His interest, his latest interest, or his main interest, is relationship between mathematics and QFT, quantum field theory. And his current project is trying to unify not string theory but space-time with twistor theory. Okay, so we're going to learn a little bit about twistor theory today. Okay, he hasn't won many medals. He doesn't have too many of them pinned on his lapel, and I don't know, maybe he has. I just haven't found any. But that doesn't take away from him. Believe me, if a person is an expert in their own field, it doesn't matter how many medals he's won over his lifetime. Maybe they missed him when they gave out the medals. He does carry a blog, Not Even Wrong, and that's a famous phrase. And he's using it to belittle string theory specifically. He goes against string theory. He says it's not even physics, so it's not even wrong. Okay, and we talked a little bit about string theory the other day. Okay, so what is this string theory? In order to answer that question, we have to go to Mr. Woit's mentor. And this man is Roger Penrose. He won a Nobel Prize this year in mathematical physics. Something very important for mathematicians, apparently, and not important in physics at all. We don't have beauty contests in physics. We don't win any gold medals like they do at the Olympics. We don't give any medals, gold medals, for knowledge, okay? Especially when people don't know. Okay, they can't explain gravity, they can't explain light, they can't explain anything out there, magnetism, electricity, but they get medals. Makes you kind of wonder. So no, we don't worry too much about medals. But yeah, this fellow, his name is Roger Penrose, and he did win medals. And this is him. I think some of you have heard of him, more or less. Okay? And Mr. Penrose is famous for inventing, or discovering, or inventing, I guess, the tribar, and also known as a Penrose triangle, and also the staircase. He also did some work with Stephen Hawking on the singularities, on black holes. He's wrote a paper on whether singularities are naked or not, whether they cover their shame. Okay, but the subject concerns us today. He also started that one. Is this twistor theory? Okay, it looks something like that. Okay, and we'll find out what that's all about, or try today to figure it out. Okay. Well, this is where Mr. Penrose starts his presentation on twistors. He starts saying that the following. He says, usually we think of space-time where space is 3 dimensions and time is another one. Okay, you've got this space-time, which is 4-dimensional structure, and the basic thing is that it is made of these little points we call events. Okay, no dimension in space, no dimension in time, but you see it like that. Those are the points in space-time, events. Well, I don't know about that. You know, I mean, when you go and see Stephen Hawking, which he died a couple years ago, he says something else about events. He says the following. He says an event is something that happens at a particular point in space and at a particular time. So one can specify it by 4 numbers or coordinates. And so the question is, you know, an event is something that happens. And an event is not a point like you see there. Is that what a point is? Is that what Mr. Penrose is referring to? Is he referring to a dot? Is that the one he's going to be using? He's saying that this space-time thingy, whatever it is, it's made of points. What is a point? Well, a point is something that happens. Well, something that happens does not happen at a location, because happens requires at least 2 frames of the universal movie. So you can't talk about location in terms of something that has motion. Motion and location cannot be reconciled. One is a static concept, the other one is a dynamic concept. He also seems to have problems with dimensions. He's really talking about number lines. You know, a number line is not a dimension, a coordinate, or a vector, not of physics. If he's going to talk about number lines and keep it within math, no problem. He can call them whatever he wants over there. But once he crosses the line into physics, he's got to use the dimensions, coordinates, and vectors of physics, not the ones of mathematics. Okay? What he's talking about is number lines. And number lines are not dimensions, coordinates, or vectors. And he's probably thinking about that little space-time diagram you see there, the famous fishnet of relativity. Okay? So, you know, again, he starts out on the wrong foot to try and explain to us this thing he calls space-time that is made of space and time, which is made of events. Those are all concepts. We don't make things in physics with concepts. Hopefully all objects, hopefully physics is done with objects, and all objects have some image that you can see, you know, that it has shape. Okay. Okay, Mr. Penrose continues. Okay, he continues and he says the following. He says, in Twistor Theory, that's not the basic structure, space-time, right? The basic thing is something like a photon. Okay, let's find out what this photon thingy is. It goes along at the speed of light, and you can identify the points because you have a family of them going through that point. Okay, photons can spin left-handed or right-handed. And you can describe the wave function of a left-handed one or a right-handed one, okay? Usually you add them together because their spins combine to give you the linear polarization. That's the way photons work. Photons can spin? Well, let's find out. Let's look up this word photon. Let's see what a photon is. Maybe I've got it wrong. Let's find out. Photon is a type of elementary particle, massless, made of energy. It's dimensionless, lacks spatial extension, lacks internal structure, does not take up space. Well, it seems like they're describing absolutely nothing, which is what you see on the bottom. This is a photon according to mathematical physics. So how can it have spin, meaning some kind of angular momentum? How can it have motion if it's a nothing? So far they described nothing. It has no mass, no size, no volume, no radius, no diameter. What is this? Well, we're talking about nothing. In fact, if it's made out of energy, and energy is a concept, we don't know of any object that is made out of concepts. So we have a little bit of problem already from the start. Mr. Penrose does not seem to know what a dimension of physics is. He confuses it with the number lines of mathematics. And he also seems to confuse a photon for a thing, for an object. You know, in physics, we have to have an object. Otherwise, you're putting a spirit in there. If you put a concept, you can't say that you transferred information. Not in science. Maybe in religion you can do that. You can say you can transfer the spirit, you can transfer the soul, you transfer conscience. You can transfer all kinds of concepts in religion. In physics, you must have an object that can do the motion. Only objects move. Okay? Motion, two or more locations of an object. You have to have an object before you have motion. Okay, so he's moving a nothing. He's moving a photon, which is apparently made out of energy, but that's irrelevant aside from the fact that it's a concept. He's moving that which has no size, no shape, no anything, no mass. What is he moving? What are we talking about? And so so far we started on the wrong foot. No dimension, no object. Okay, let's continue. Let's see where this leads. Okay. Here, Mr. Penrose continues. He says, in Twistor's theory, you have 2 different formulae, one which works for the right-handed one and one which works for the left-handed one, just like the photon. For the gravitons, the particle of gravity, you want to make it fit in with Einstein's theory so it changes space. Space-time is changed by the gravity. Okay, so remember space-time, you warp the canvas. You have to put something on the canvas, warp it downwards, you create the depression, and that becomes gravity. So you create gravity with gravity. You create the depression by putting something in there, in this case a bowling ball known as, what, a graviton, okay? And you curve space-time. Now anything that's close to that will fall inside the hole. That's That's the notion that these people have. Okay, you find you can do it for the left-handed ones, but not for the right-handed ones. Okay, you can do it for left-handed gravitons, but not for right-handed gravitons. Okay, left and right are not quite the same in the theory. You can do the left-handed ones, but not the right-handed ones. You're trying to get the right-handed ones in the framework which does the left-handed ones. Okay, so this is what they're trying to do mathematically. Okay, let's keep that in mind. It's all, so far we're talking about no object. We still don't know what a graviton is, but maybe we'll find out soon. But the question is, there's an issue there with left-handedness and right-handedness. Apparently electrons can do it, but and photons probably do it, but gravitons cannot. Okay, let's continue. Let's see what else Mr. Penrose has to offer here. And yeah, he said this is a way of describing physics, which is unusual. Yeah, I bet it is unusual. I mean, so far we have nothing. We have a confusion between the dimensions of physics and the number lines of mathematics, so that we started on the wrong foot. But now he's saying that this is a way, an unusual way of describing physics. I agree. If you can spin both of them left and right like that, you can do also the particle interactions, the strong interactions, the weak interactions. You can put the right and the left together. Okay, so there we have a particle interaction. It's using a Feynman diagram. We have space-time, space versus time. They usually put all three so-called dimensions, as they call them, number lines on the bottom, on the horizontal axis, and they put the number line known as time, something that belongs exclusively to math, has nothing to do with physics whatsoever. We don't have any use for time. We only deal with objects in physics. And they have time running instead of height. So it's a weird way of doing physics, no doubt about it. They have, I guess on the horizontal axis, we have width versus time. What sense does it make? Time doesn't have direction, but here they put it as a direction. Okay? So again, they're talking about number lines, not about physics, not about dimensions, not about coordinates, not about vectors. We're talking about number lines. Okay, let's keep that in mind. If you can spin both of them left and right like that, you can do also the particle interactions. What particle interactions? Here we have a particle interaction. We have an electron moving upwards here, right? And it throws a photon at another electron, pushes it away. Great, no problem. We're going to understand push. The problem quantum mechanics has is explaining pull. How do you explain pull with this Feynman diagram? How do you attract? I mean, if two rocks throw gravitons at each other, right? This is what we want to understand, the mechanism. If they throw gravitons at each other, right? Cast gravitons, how do you pull with those gravitons? There you have a particle interaction. Particle hits particle. Okay, so where's the attraction? How do you pull with that? This is the big problem that these people have. They can't explain the force of pull. And in fact, he talks about the strong force. Here's the strong force, the gluons, okay? And you can see that the gluon is, it's illustrated as a spring, as a bed spring, okay? So yeah, we can all understand how two rocks can attract each other. If there's a bed spring between them, we can all understand pull. But when you look at the standard model, you don't find bed springs. All you find is little balls. You find gluon balls, not gluon bed springs. And what they do is they say, look, the gluons spread apart, and they create these these elastic bonds, which I don't know what they are. What are those? What is that thing that is stretching? Bubble gum? I mean, what is this? Where do you find this line, this elongated entity in the standard model? That's the question. Okay? And you can see what they do. They replace those things when they talk. They replace them with concepts. They say, look, the energy required to separate quarks produces quark-antiquark pairs, long before they are far enough to observe separately. Okay, so what they're saying is that you stretch energy, whatever energy is. Mr. Feynman told us that he didn't know what energy is, of course, because energy is not a what. It's a concept. There is no thing called energy. And so they're going to stretch this non-thing, this concept. They're going to stretch love. They're going to stretch, intelligence here. And by doing so, they create a quark. And what is a quark? I guess a bunch of energy, more energy. So again, they're doing all their physical interpretations with concepts. And we don't do physical interpretations with concepts in physics, because you need objects to explain mechanisms. We're trying to find out what the mechanism of gravity is. Remember that? That's what we were trying to do here. And these people are saying that they can do attraction between quarks, between rocks, between whatever, but whether it's the graviton in the case of rocks, whether it's the gluon in the case of quarks, and they're not explaining the mechanism. They're not saying what keeps those two quarks together. And so they say, well, it's energy. And the way they put it is in reverse. They say, if you try to pull two quarks apart, all you're doing is stretching the gluon, and that creates more quarks. And what is a gluon? A bunch of energy. Great. We learned a lot. Okay? Yeah, they treat all this stuff mathematically. And so they have no physical interpretation for what they're doing, and that's why they have to invent these explanations, these theories, if you can call them that. Okay? Physical interpretations. Okay, Mr. Penrose continues, and he says, it has the sort of features which appeal to me very much. Okay, one of them is the use of complex numbers. Oh, hey, what is a complex number? Let's find out how complicated this is. Which includes imaginary numbers. And that's the imaginary number, which is the square root of -1. It's known as an irrational number. So they do what they do is they multiply everything by a rational number and an imaginary number, and now they continue doing math. Okay, and that's what they're going to use. In fact, he states that for quantum. He says once you put that into it, you have a whole different way of looking at the world. No kidding. The thing about it is that quantum mechanics already looks at the world that way. So quantum mechanics can't do without its square root of -1s. Okay. The states in quantum mechanics already involve these complex numbers, meaning irrational numbers. So the idea is that you bring that kind of complex number geometry into the real world. You're going to bring all this abstract stuff, and you're going to say it's part of our real world. Okay? And somehow the quantum and classical worlds will get a bit mixed up. Yeah, there's very beautiful mathematics in the complex world, which you don't see in the real world. Well, are we talking about the real world, or are we talking about an imaginary, complex, inexistent world? I mean, the real world is the existing world. What are you talking about? I thought we were going to do physics here. I thought we were going to explain, what is it, gravity? So let's find out. Yeah, sorry, you got the wrong one there. He says the following. He said how he got into this math thing. Okay, he says, and that's what Twistor Theory does. It gives you a complex number, real and imaginary together. Imaginary meaning also irrational. That's also what it's called. Includes that. A picture of the world which involves quantum ideas as well as classical ones. Okay, so they're trying to. Classical means you're going to try to imagine the theory, and that's what they're trying to do. They're trying to imagine the theory. Okay, they have a mathematical description. They're going to give a physical interpretation, and what they're saying is that this playing around with the equations by introducing imaginary numbers and irrational numbers, really complex numbers, what it will allow them to do is really make sense of quantum mechanics. That's what they're trying to do, okay? And they're going to apply it to gravitons, of course. When I was a mathematics undergraduate, I was absolutely stunned by the magic that there is in these complex numbers. Okay, so you were wowed by mathematics, great. 1 + 1 = 2. It's a tautology. So this is what mesmerizes them, hypnotizes them. Wouldn't it be nice if somehow that was what governed the world? Yeah, I mean, idealism, maybe a little bit too much. Okay, this is what Mr. Woit does with this. He does. I mean, Mr. Woit is an expert in math, no doubt about it. And he's writing 2 papers, or I think he wrote them. I don't know if he's about to publish them. And here they are. You see them real quick here. And what I want you to notice is that in this paper, hyperfunctions and imaginary time, quantization, whatever that is all about, you can see there's no pictures in there. There are no pictures. All you see are equations. And you would think that if he's going to talk about twistors, I guess that he's trying to explain gravity, you would at least see one picture somewhere in that paper. Never will you see a picture in a published paper of these people. All you'll see is a bunch of equations. And so people out there, 99.99% of the people out there, they don't care about equations. They say, okay, give me the bottom line. I want to know why this pencil falls to the earth. Okay, why it falls to the floor. That's all I want to know. Just give it to me straight. How does that work? And these people say, well, you got to take, you got to look at hyperfunctions to understand it. You got to look at imaginary time. And you got to learn a lot about Twistor Theory, at the university level, PhD level, to really, really understand it. And so here we have these group of people. There's 5 of them on the world, and they talk about Twistor Theory because they are experts in Twistor Theory, and nobody knows what they're talking about. Then you have the other group over here, the string theorists. They talk about their strings. These guys don't talk to them. The other guys don't talk to these guys. And so we have the Twistor mathematicians and we have the string mathematicians. Each one developing equations out there. And you just ask them, look, I'm just very humble. I just want to know why the pencil fell to the floor. And they tell you that you have to take a course in math. And you say, well, hold on, I just wanted to know the simple, here's a pencil and here's the earth. We know that the pencil is attracted to the center of the earth. What attracts it there? All I want to know is what attracts it there. And it seems like all you need to do is figure out what invisible entity is coming in contact with the skin of the pencil. That's how simple it is. And these people are saying, no, you need to understand all this math. You say, but, it's counterintuitive that I would need all this stuff. You would think that it's more intuitive that all you need is some identify the invisible physical object that's pulling or pushing the pencil. And the answer they give you is that, well, Father Universe doesn't agree with our intuition. Your intuition is wrong. And who says that their intuition matches Father Universe's intuition, or the way he does things? Does this math represent how he does things? And I don't mean by how, a description, I mean how, the cause, the mechanism. I want to know the mechanism of gravity. And these people are giving me a description and saying, well, that's important, and here's the explanation. The explanation is warp space or gravitons. Yeah, but you can't explain it with gravitons. And warp space, warp time is a concept. You can't say that you're going to warp time and that prevents the Earth from flying out of the solar system. And they say again that your intuition is wrong, that Father Universe doesn't think like you. And again, does Father Universe think like him? Is that what he's suggesting? Is that what he's implying? And here's another paper by this gentleman. And this, again, I guess he's going to be publishing it soon, or he's about to publish or whatever. This is a draft version, and he's got on his website, blog. And what do we see? We see equations. Nowhere do you see a picture. So it's all like that. It's all non-pictures. And you would think that physics is about pictures. Physics should be, you should be able to explain physics, simple physics, like mechanisms, to a baby. These people say, well, here's the explanation. But all the explanations are irrational. They're either bending concepts, warping time, or they're throwing particles at you and saying, I attract you with that. I throw tennis balls at you, but you come closer to me. So all the explanations are irrational. You can't make sense of any of them. And so what are we supposed to do? We don't have communication because these people are doing a lot of math there. And the question is that math relevant? Is that worth anything? Has this man spent his whole life in a worthless pursuit by doing all this math? What is all this math worth if they cannot explain a simple thing as how a pencil falls to the floor? This is what you got to think about. Okay? These people make a lot of money, by the way. You're paying for their salary, so the question is whether you really want to pay for his salary. For him to do what? Equations, publish papers in which he gives a lot of equations, and he doesn't give you a mechanism, a rational mechanism. And all we need to do for a rational mechanism is to identify the invisible objects. And hopefully there are objects out there, invisible, intangible objects that Mother Nature uses to do gravity and light, because otherwise you're putting spirits in that same space and you're doing religion. So you can't come with an equation and substitute it for a physical interpretation, for a mechanism, for a cause. Okay? Okay. So what does Mr. Woit do? Well, he does particles. That's what he does. And this is what he's been educated to do. He's been trained, educated to deal with particles. They call them waves sometimes because the particles are the ones that wave. So waves also include particles. except when you're waving vectors, which is another thing that they wave. So we're replacing this and we're saying, look, all atoms in the universe are physically interconnected. That's what they've been missing all these 400 years since Robert Hooke came up with the wave nature of light. Because before that, it was all particles, 100% particles. Everybody would do particles. After the 17th century revolution, scientific revolution, they figured out that they could that light apparently had wave properties, attributes. And so since then, they've been doing waves, particles, particles, waves, waves, particles, particles, waves. So that's what we've been doing now for 400 years. And that's what Mr. Woit was trained and educated on. And he never thought or even imagined questioning that. I mean, after 400 years, are you going to question the particle or the wave assumptions? I mean, that's what everybody's been doing. So it never crossed his mind that he could question that. And he just kept doing particles and waves, really particles, because that's what quantum is. They use the wave as a crutch. When they can't explain something, the slit experiment or, I don't know, Compton wavelengths or whatever, then they bring in the wave. Or, for example, polarization. And otherwise, they always do particles. And what is a wave? The motion of particles, so we're back to particles. No matter what you do, you're always back to particles. But these are magical particles for the last 100 years. They're no longer the classical particles, the little ball. No, these are magical particles because they don't represent, the word particle is a misnomer, and they use it very handily to talk about particles because it's got that duality that you could be referring to waves, you could be referring to corpuscles, or maybe to neither, maybe just to some magical value, magnitude, an amount, which is what they're going to put in an equation. That's what the word particle means to them. So when they accelerate a particle, they're accelerating an amount. It could be an amount of energy, which is, again, an amount, not a thing. Or they're accelerating a charge. What is a charge? It's an amount, 1.6 times 10 to the minus 19 coulombs. That's what it is. It's a number. That's what they're accelerating. So these people are always accelerating numbers. That's what they do in their equations. And then they casually extrapolate that into physics, like saying, okay, let me give you the physical interpretation. You have this particle that moves at the speed of light. You say it's a ball? No, it's got no size, no volume, no mass. So what are you talking? What are you accelerating? What is accelerating at the speed of light? What is the physical object? And some of them will tell you, hey, it's the acceleration of nothing. It's the undulation of nothing. That's what a photon is. Okay? So this is what he has in mind. He has either particles or waves. Never thought about questioning any of these two. And this is what they've been doing for the last 400 years. And the question is whether either of these two meet these criteria, which are the attributes of light. Is it wavy, like in the case of particles there, the flow of photon beads? Light moves in a manner of oscillating waves. That one seems to be moving straight, not up and down like you see at the bottom, which is a bunch of vectors. Okay, so we've got a little bit of a contradiction already at the start here, because the flow of particles, the flow of photon beads does not explain the waviness that light seems to have. The bottom one explains the waviness, but what is waving? Vectors. So both of them fail. Both the particle and the wave, the transverse wave that Mr. Fresnel came up with to explain polarization especially, both of them fail. The bottom one is not an object. The top one, the particles are objects, but you cannot explain oscillating waves with that. So neither one passes the first criteria of the attribute of light. Next one, laser ranging. If you turn your laser on, 1 second later you will detect the light on the moon, approximately 300,000 kilometers away. In other words, it takes 1 second for the laser beam to hit that retroreflector that the astronauts put on the moon, for those of you who are not flat earthers and believe that humans went to the moon. Okay, it takes 1 second approximately, okay, roughly. And the question is, why can't the particles travel faster if they're going one way? Why can't the waves, the bottom waves, the two transverse waves, travel faster? I mean, what prevents them from traveling faster? That's the question, okay? Or slower for that matter, right? Because they claim that these things travel slower when they go through denser media, but then when you want them to travel faster, they say, well, they can't travel faster through vacuum. And what is vacuum? A bunch of particles. So here they go through the particles of vacuum and they can only travel at a given speed, no more. But then when they travel through other particles, the ones that we have in the real world, you could say, they go slower. That's their explanation. They have this thing called refractive index where they make a conversion of the speed of light to according to how dense a medium is. Constancy of light, they cannot explain that. Why frequency is inversely proportional to wavelength. C equals frequency times wavelength. The speed of light in a vacuum, at least they'll agree with that, is 300,000 kilometers per second. Okay, and you can increase the frequency only at the expense of wavelength. In fact, it is that difference that gives us the colors of the spectrum. Okay, ray reversibility. Mirrors reflect and refract light along what? Rectilinear trajectories or straight paths, whichever one you want. But that thing is straight as an arrow. Okay, so ray reversibility shows that light travels or extends straight. Okay. Light lines along or runs parallel to a straight axis. Amplitude, light obviously has it. And then you have Faraday and Maxwell laws. One field, so-called field, magnetic field induces the electric field and vice versa. How do particles explain that? How do they explain these attributes of light? So particles is a bad start. And waves is a no-brainer either because you can't start with waves because you got to identify what the physical object that is waving. Waves is a verb. There is no physical standalone object called a wave. Okay, so what do we propose instead? Well, here it is. Does this one pass the attributes of light? Let's see. Let's find out. Well, it looks like it does. We're saying that what we have here is two atoms. One is two-dimensional, the other one three-dimensional, just so you can see how it's built, how it's constructed more or less, okay? And they're connected by a rope. They're physically connected by a rope. The rope is a physical entity, not a field. Field is a concept. There is no physical object called a field. But a rope is a physical object. You don't believe me? Go to the hardware store and ask for a rope, and they'll give you a rope, a two-strand rope. They'll give you something that looks more or less like that you're seeing there. Ask them for a field. Let's see what they give you. What do they give you? A football field? So there is no physical object called field. But rope, yeah, there is an object called rope. And it's made out of two strands, two physical strands. And that's what we're proposing binds any two atoms in the universe. So all atoms in the universe are physically interconnected. Does it pass all these attributes of light? Obviously, it's wavy. Okay, a rope is wavy, already structurally wavy. It tells you why it goes so fast at 300,000 kilometers per second. Why? Because torsion is the fastest thing imaginable. 3D torsion, not a 2D transverse wave, but a 3D torsion along a physical medium. Okay, so now we have a physical interpretation for light. Is it constancy of light? Yes. C equals frequency times wavelength. The shorter you make the links, the more links you can get for any length of rope, and vice versa. Okay, so C equals frequency times wavelength is the equation of a rope, not of a transverse wave. Ray reversibility always travels straight because it's taut. It's a taut rope. It's stretched to the limit. That also gives you the reason why C is a constant everywhere. Little c is a measure of the tension on the rope. Okay, and so the rope is constantly under tension. It's pulled by every atom in the universe is pulling on that rope through other atoms. Amplitude, obviously, you can see the amplitude there, and you can see why one induces the other one into being, or why it misled the mathematicians to believe that one induces this thing they call field into being. And one of the problems with mathematical physics is, and that goes especially in regards to Mr. Woit, and that's that what these people do is they believe in experiments. So they do an experiment. They can't see or touch the mediator that Mother Nature uses for gravity, for light, for magnetism. They can't see or touch that. So they infer it indirectly. And for the last 400 years, we've been doing indirect assumptions based on experiments. What does that tell us about experiments? Well, it tells us that we don't need experiments in physics to determine the invisible, intangible mediators that Mother Nature uses, or Father Universe, whoever you pray to. Okay, you're not going to discover them through an experiment. The only way to reach an agreement with Mother Nature or Father Universe is to visualize. You have to see. You have to use the mind, not the eyes, not the hands. You got to use the mind. You got to see, you got to say, what could Mother Nature be using to do light? What could Mother Nature be using to do gravity? And it better be a what? Better be an it. Better be a thing. Because otherwise you're putting spirits in that same space. You're using black magic. And when you use concepts, it's even worse, because now not even God can do that. You know, you can't say that you sent energy, or that you have a field between two objects, or that you have mass. How does mass pull on another mass? Does it send mass, throws mass at it? Does it throw energy? Does it pull through the field? Field is a bunch of numbers. So you can't use concepts as physical objects to give a physical interpretation. All those words, you can keep them within math. We have no use for them in physics. When you come across the line into physics, you got to use the language of physics. And that's where all concepts die at that line. As soon as you cross that line, forget about all your concepts. Now you got to give us a physical interpretation. We want to know how gravity works. We want to know how light works, what the mediator of light is. We want to know what this thing you call field is. We want an object on the screen or in person or whatever. Maybe you can show us what a field is. You can bring it to the conference. Show us exactly what a field is. Don't tell me that you got a field and this is the equation. We don't care about that. Okay. Okay, and here's, not only do they fail with light, they fail with space. And I don't know what notion Mr. Woit has of space, but obviously he's got some notion. I mean, he's going to try to merge his Twistor theory with space-time, right? That's his goal. This is space-time. There you have space and time. A little fishnet, canvas, trampoline, whatever. He's going to bend it with mass, I guess, because that's what general relativity does. I mean, if he's going to merge both of them, he's going to rely on this model. We wonder why the moon doesn't fly out of the solar system. Okay, so it keeps going around the Earth. Why doesn't it fly away? What keeps it bound? Well, general relativity says there's a depression caused by the mass of the Earth bending downwards, space-time. Then they tell you, well, don't pay attention to that. You're not supposed to take it so literally. No, I gotta explain why the moon doesn't fly out of the solar system. Tell me what physical entity stands in the way of the moon flying out. Is it warp time? Is that what you're going to tell me? So again, we have a problem because the physical interpretation is irrational. They're using a concept called time. They're warping it, and they say that's why the moon doesn't fly away. And then when you say, well, that's irrational, he says you're not supposed to take the analogy so literally. So they take away time at the end when you say, well, it's a concept. Yeah, it's a concept, but that's how we explain it. So it's an irrational explanation. It makes no sense whatsoever. So don't try to imagine it or even try to understand it. You can't understand it. And that's why they say, well, you got to take math to understand it. Yeah, because not in physics, maybe in math. Okay. So Mr. Woit probably believes also in this, that maybe space is some kind of ether, maybe a bunch of particles, or like, what was it, Mr. Laughlin, Nobel Prize. Also, he says, what we use in quantum mechanics and in mathematical physics in general is an ether, but we don't call it that because it's taboo. The word is taboo. They can't use the word ether, but that's what they're referring to, a bunch of particles. What's the wave? It's a waving of particles. So I don't know what other thing Mr. Woit could be thinking of when he's thinking about space. It's either that space-time canvas or maybe a bunch of particles. I have no idea what he would think space is. Okay? And so we ask Mr. Woit, what is space? Can you tell me what space is, or define the term, or whatever? Point to it, or whatever? And these are the questions that, or the answers you'll find on the internet. Maybe one of those is the one he's referring to. I don't want to put words in his mouth, but almost surely he's got one of those. Okay? The boundless three-dimensional extent. What's an extent? Is it a physical object or an abstract concept? Physical space. Physical is an object. Space is nothing. So we have a something and a nothing. Great. Something, nothing. That's what he said. Or someone said that. Physical space. Is that what Mr. Woit is going to present? Physical space? Something, nothing? 3D space. A geometric setting in which three values are required to determine the position of an element. Point. And again, we found out a point. What is a point? Is a point a dot, or is it a location? I mean, if it's a location, don't call it a point, call it a location. And if it's a dot, call it a dot, a two-dimensional dot, or three-dimensional ball. I don't know which one they want to use for location. So you either talk about location or you talk about the object. And what they did, they condensed them into the word point. And so the word point is one of those dualities that mathematicians like because it means both things. It means the object, dot, and the concept, location. They love that because they can now give a pictorial representation within their presentation, within their dissertation. Okay, in 3D space, well, space is nothing, so there is no such thing as 3D space. Okay, space has no dimensions whatsoever because it's nothing. Objects have 3D space. Objects have 3D, 3 dimensions, physical dimensions, like in other words, the dimensions of physics, right? Length, width, and height. Only objects have this. Space has no length, width, or height. Okay, space is nothing. Vacuum, space devoid of matter. Great. And vacuum, you look it up and they'll tell you that vacuum is made out of particles. And there you see some examples. The quantum vacuum, the quantum state with the lowest possible energy. What is energy? A concept. There's no such thing as energy. So whatever energy is, it's got very little of it. Quantum foam, fluctuation of space-time. So here you have this concept and it's fluctuating, vibrating, I guess, right? That's what quantum foam is. What is quantum foam? That's another version of space. Dirac sea, another version of space. The vacuum as an infinite sea of particles with negative energy. You have positive energy when you feel great and energy when you're down and out, I guess. I mean, what is this negative energy? Just a mathematical concept. And that's what this vacuum that Dirac invented is made out of. And what is it? Virtual particles. Particles that combine to form nothing, and then they separate to form 2 particles. So we have a nothing made of 2 particles. Like I always say, you have a black and a white ball. They get together and they form no ball. And then the no ball separates and forms a black and white ball. That's what these people are saying. So they have all these vacuums, all these spaces, all these nothingness. And all the nothingness are made out of something, all of them. There's not one nothing space vacuum in all of mathematical physics that is total nothing. No, all of it is something. There's no such thing as void in mathematical physics. They had to put a background because they can't otherwise explain any of the things that they do, any of the phenomena. They can't explain all the any of the invisible phenomena. How do we do it in rational science? Well, we do it a little different. What we do is we define terms so that we talk sensibly. We can talk consistently, rationally. Foundations of physics, the first principle is the golden principle. Physics requires an object. You can't do physics without an object. Something all these mathematical physicists have never learned in 400 years. Yes, we don't use math, we don't do experiments. What we have is to define what an object is for the purposes of physics, because you can't do physics without an object. What physics are you doing? What are you analyzing? What are you measuring if there's nothing in front of you? So yeah, you had better have an object before you do physics. And something, which is an object, right? That which has shape. What is nothing? That which doesn't have shape. Now we can use these words consistently, rationally, scientifically. Something is the opposite of nothing. They're antonyms. And there I gave an example. Something is that black stuff you see there. Whatever it is, it's got shape. And nothing is the one next to it, which is that which doesn't have shape. See how easy it was all these years? All you have to define is something and nothing. Space is nothing. Space is that which has no shape, which means particles have no way of escaping space because space has no boundaries. Not because it's infinite, but because it's not an object. Infinite is an adjective, and in science we can only apply adjectives to objects, and there is no object which is infinite because all objects are finite. We're done. See how easy it was? All you had to do was define the term so that you can talk sensibly. And so we have nothing, which is space, and we have all this matter, all these atoms that are just floating with respect to each other in the nothingness we call space, which has no boundaries. Therefore, space cannot turn into matter, matter cannot turn into space, and there was no beginning to the universe, as general relativity, what Mr. Woit believes in, says. Okay. Just one more issue here, a couple more issues. Here's Mr. Woit cannot use any of these to define the word object. He cannot use these criteria, okay? He cannot use see or touch because that requires 2 objects. Mass requires 2 objects. You got to weigh something to determine its mass or count the number of atoms or whatever unit you're going to use for a mass. Fine, you got to count them. You got to tell me the difference between an elephant and a chair. Okay? And you say, well, the elephant has gazillions of made of gazillions of atoms. The other one is just 1 million atoms. Okay, fine. So you got to tell me what an atom is. You got to count them. So again, mass is counting. Motion, volume, same thing. All of them require, all are dynamic concepts. Made of, again, we don't care what something is made of. It's called mereology. We don't say that a table is what it is made of. No, table is what I point to. That's a table. What it is made out of, it's made out of atoms, just like an elephant is made out of atoms, just like a house, a tree, a rock, they're all made out of atoms. But I have to distinguish the words, so I got to find out what an elephant is different than a table. If I have the ET come to Earth, I have to teach him my language, and I can't use and say, well, it's what it's made out of. That's a gazillion atoms, that's 1 million atoms, that's a billion atoms. No, that's not an object. That's a table, that's a tree, that's a rock. That's the way we do it in physics. We point to objects because what? The only property that all objects in the universe, whether they're two-dimensional or three-dimensional, have is form, shape. Okay? And yes, the words form and shape mean the same thing in physics, not in ordinary speech and mathematics, right? What they do in ordinary speech and in mathematics has nothing to do with physics. In physics, shape and form mean the same thing. In fact, in Spanish, we don't have a word for shape. We only use the word form, forma. Okay? So we only have form for everything. So we don't have this shapey thingy that people made a distinction in ordinary speech, which came out of mathematics, out of geometry. Okay, temporal, see something by parts. We don't do that in science. Again, temporal is when you don't look at the table in one shot, you look at it piece by piece. There are no observers in physics. We don't accept testimony, witnesses, none of that. So we don't care what you saw. Okay. Now, an object is that which has shape before we put an observer to see it, piece by piece, time by time, second by second. No, it's not a noun. It is a noun only for physics. Only that which has shape qualifies as a noun. The word motion is a noun in ordinary speech. It is not a noun in physics. So the word orbit is a noun in ordinary speech. That's not a noun in physics. In physics, orbit is a verb. Wave is a verb. Field is a verb. Energy is a verb. None of those are objects, standalone objects. Standalone objects you point to. Can you point to energy? Can you point to some kind of shape known as energy? Absolutely not. Can you point to mass? No, you can't. You got to count mass. If you're counting atoms or units of mass or whatever. Color needs a vibration, some kind of motion of light in order to see color. Frequency versus wavelength. It's not an object is not a synonym of exist. In addition, you need location. So an object with location is a definition of exist. And it's not 3D because we have 2D objects and they're known as squares and triangles and so on. So no, 3D is not an object. That's in ordinary speech, not in physics. Okay, physics, shape. It's the universal property of all objects. And here we go with the last one, and this is why the Earth doesn't fly out of the solar system. It's because all atoms of the Earth are bound to every single atom of the sun. The sun twirls the Earth around like a bunch of Lilliputians would twirl Gulliver at the end of ropes. That's why the Earth doesn't fly out of the solar system. Okay? So, I don't know if you should contribute to, what is it, Twistor Theory? By the way, these people are a dying breed, those who are pushing for experiments. Like I mentioned, Sabine Hossenfelder and Nobel Prize winner, what was his name? Sheldon Glashow, Mr. Woit. They're all dying breed of people because everybody's moving on to string theory and leaving them behind. Are they doing any better? No, of course not. As I showed that Mr. Maldacena a couple weeks ago, he's not doing any better. He's getting into more abstraction. He can't explain gravity any more than Mr. Woit can. Why? Because they're all using the wrong hypothesis. They're all starting at the wrong point. They're starting what? With particles and waves. Once they abandon that assumption and they assume that all atoms are interconnected, then maybe they can make a little bit of progress. Why can't we see or touch the mediator of gravity, of light, of magnetism, etc.? We can't because Mother Nature specifically made them invisible and intangible. And so you won't be able to go to the lab and figure out what light, or gravity, or magnetism, electricity, any of those are. Not by running an experiment. The experiment for gravity, here it is. You'll never need another experiment. Here, we let go of the pen, Okay, do it again. How many times? Repeatable experiment. Let's do it a million times. Okay, there it goes. That's the only experiment you ever need. Now you know what gravity is. Gravity is that something that pulls the pen down. What you got to identify is the physical object that came in contact with the skin of the pen. And we say that all atoms of the pen are connected to all atoms, or every atom that comprises the Earth. That also explains why gravity goes through things. Okay, why one atom is behind another atom. So yeah, we do have an explanation, a physical interpretation for gravity. We have a physical interpretation for light. We have a physical interpretation also for electricity and magnetism, as I showed the other day, and for the workings of the atom. Now, again, people get stuck on this see touch. They say, why can't I see and touch? They say, how do these ropes cross each other? Because not all objects you can see or touch. Not all objects have the property of touch. The rope does not have the property we know as touch, as we see the ropes, ordinary ropes, in our ordinary lives. In our ordinary lives, you know, you can't have a rope go through another rope, like this, for example, right? They can't crisscross each other. In Mother Nature's universe, that property is missing from the rope and from the threads that make up the rope. So the rope does not have the property of touch. And that's a big can of worms. I explain that in my book, Why God Doesn't Exist. There I explain how something which is a rope, the electromagnetic rope, acquires the properties of touch and of see, you know, that you can see it eventually, atoms and upwards. Okay?